Good morning, everyone. I want to start with a question that sounds absurd on its face. Can hot water freeze faster than cold water? Your intuition screams no, and frankly, so does the first law of thermodynamics. Yet this question has haunted physicists for over 2 millennia. Today we're going to explore the Mpemba effect, what it is, who discovered it, why it might happen, and why, even in 2026, the scientific community still cannot agree on whether it's real. Buckle up, because this is one of physics' most delightfully stubborn puzzles. Here's our path for the next several minutes. We'll define the paradox precisely, because definitions matter enormously here. Then we'll trace its history from Aristotle to a Tanzanian classroom in 1963. We'll examine the proposed mechanisms, confront the fierce criticism head-on, look at where the effect does seem to appear, and close with where the scientific consensus stands today. Fair warning, if you came for a tidy resolution, you might leave frustrated. And that's exactly the point. Let's start with the core claim. Take two identical volumes of water, one at 90 degrees Celsius, one at 30 degrees Celsius, and place them in the same freezer. Common sense, backed by Newton's law of cooling, says the colder one must freeze first. It has less thermal energy to shed. But under certain conditions, multiple experimenters have reported the opposite outcome. The hotter sample freezes faster. This is the Mpemba effect. I want you to sit with how uncomfortable that makes you feel, because that discomfort is exactly what makes this phenomenon so fascinating and so fiercely debated. Here's the working definition used by most researchers. Two water samples, identical except for their starting temperatures, are cooled the same way in the same environment. The Mpemba effect is observed when the initially hotter sample completes the cooling process in less time. But notice that last bullet, there is no universally accepted definition. Some researchers measure the time to reach 0 degrees Celsius. Others measure the moment visible ice first appears. Still others include the full phase transition. This definitional ambiguity is not a footnote, it's central to the controversy. Different definitions produce different results, and this is where much of the confusion lives. This is not a new idea. Aristotle, writing around 300 BC, observed people wanting water to cool quickly would first heat it. He noted this in his work Meteorologica. The puzzle pops up across centuries. Medieval European scholars wrestled with it. Francis Bacon tried experiments in the 1600s. But by the 20th century it had been largely dismissed as folklore, until a Tanzanian high school student named Erasto Mpemba noticed something strange while making ice cream in 1963. His persistence in the face of ridicule brought the phenomenon back into scientific discourse. The timeline itself tells a story about how knowledge gets lost, dismissed, and rediscovered. This story deserves attention because it's remarkable. A teenage boy in Tanzania, laughed at by his own teacher, who literally coined the phrase Mpemba physics as an insult, refused to accept the dismissal. When Dennis Osborne, a physicist from University College Dar es Salaam, visited the school, Mpemba stood up and asked the question everyone had mocked him for. Osborne, to his credit, took the question seriously. He ran experiments, confirmed the effect under certain conditions, and co-authored with Mpemba. Think about that. A high school student from a country with limited scientific infrastructure became the namesake of a genuine physics puzzle. The courage of that moment is worth celebrating, regardless of where the science ultimately lands. So, if the effect is real, what could explain it? No single mechanism has one consensus, but researchers have proposed several, and they're not mutually exclusive. Evaporation is straightforward. Hot water loses mass, so there's simply less to freeze. Convection means the temperature gradient inside hot water may drive circulation that speeds cooling. Dissolved gases. Hot water holds less dissolved gas, which changes its freezing behavior. Supercooling is especially tricky. Cold water sometimes stays liquid below 0 degrees Celsius, while hot water bypasses this state. And if you set a hot container on frost, it melts the frost and creates better thermal contact with the freezer shelf. Each of these has experimental support, and each has experimental refutation. Now we arrive at the firestorm. The skepticism is not fringe. It comes from serious physicists who point out something inescapable. The Mpemba effect, appears to violate the first law of thermodynamics, perhaps the most ironclad principle in all of physics. If a hotter system can cool faster than an identical colder one under identical conditions, you've essentially got energy disappearing faster from the hotter system, which would, in principle, enable a perpetual motion machine. That's a huge claim. The skeptical view, articulated forcefully by the skeptical inquirer and supported by controlled studies, is that what looks like the Mpemba effect is actually the result of uncontrolled variables. Yet proponents point to cases where the effect has been replicated. We're left with a reproducibility crisis in miniature, and it's genuinely unresolved. Here's where the story takes an interesting turn. While the water debate rages on, physicists modeling systems far from thermodynamic equilibrium have predicted that Mpemba-like effects should occur in a wide variety of materials, and experiments appear to confirm this. Crystalline polymers, ice-like solids called clathrate hydrates, and even certain magnetic materials undergoing cooling have all shown the effect. This suggests something profound. The Mpemba effect may be a genuine feature of out-of-equilibrium physics, but water, the very substance that gave the effect its name, may ironically be the worst place to look for it. Water is thermodynamically weird in many ways, and those very anomalies may obscure the underlying physics that the Mpemba effect hints at. So, where does that leave us in 2026? The honest answer: unresolved. The Mpemba effect in water remains neither confirmed nor definitively disproven. It occupies a strange liminal space in physics, where replication is spotty and consensus elusive. But here's what I want to leave you with. The question may matter more than the answer. This puzzle has driven physicists to develop better models of non-equilibrium thermodynamics, study new materials, and sharpen experimental methodology. It's also a cautionary tale about scientific hubris, about the impulse to dismiss anomalous observations because they don't fit our theories. And at the center of it all is Erasto Mpemba, a teenager who refused to be told what physics is and isn't. That, ultimately, is the spirit that moves science forward, whether or not hot water freezes first.